I'm delighted to present our research, pixels, regions, and objects, multiple enhancements for salient object detection. The aim of SOD is to mimic the human visual mechanisms to identify and segment the most eye-catching region in an image. It is the fundamental of many high-level visual tasks, such as object recognition and scene understanding. However, accurately detecting object positions and boundaries are not so easy, especially when there are partial obstructed objects, multiple connected objects, camouflaged objects, and tiny objects. An intuitive solution for adjusting this problem is to explore the mechanisms of the human visual system. Here are some mechanisms which have contributed to SOD tasks: boundary sensibility, content integrity, structure sensibility, visual spatial frequency model, iterative refinement, and cognitive bias. Okay, here is the structure and pipeline of the proposed MENet. We firstly employ the image frequency decomposition theory and design a true string features learning structure with two ME modules as the core. The two MD modules have the same structure but have different functions. The gradient ME modules are supervised by the frequency decomposed GT map to enhance boundary accuracy, or in other words, high frequencies, while the other branch are adaptively learning inner body features, low frequencies. This is different from the existing two-branch or edge-aware methods that normally use one branch for the boundaries and the other one for the entire object. We let no information exchange between the intermediate layers of the feature block between the two branches in one training run to reduce the interference of inaccurate information with each other. Next, let's take a look at the detailed structure of any module. The grade rate uses multiple scale or frequency features layers by 5 stages. Each stage consists of an ASBP and an attention module. ASBP diversifies visual fields and attention to emphasize locations. What's special is that the ME module can output high and low level features merely by changing the input order of multi-scale feature layers in terms of their spatial size. So, taking advantages of this, we can design a multiple enhancement training strategy for the network to mimic human interactive enhancement mechanism. Let's take the adaptive MD model as an example. ME model has 3 ports. The first port for background features, the second and the third for the features from previous runs. After each run, high and low frequency features, the boundary and global features are concatenated into a full bench settings map, and then the full bench features is injected into the two ME modules respectively to participate the next round of the feature fusion. In figure 6, we first inject sublayers from large to small, then reverse order each time. So the first and the third one, that is k equal to 1 and 3, is check the global features, while the second and the fourth one, that's k equal to 2 and 4, is check the detail accumulatively. In this way, we can see global and detail features complement each other and promote each other. Loss function also play a crucial role in our model. We propose a new hybrid loss, which is composed of a pixel level, region level, and an object level loss. Pixel loss is the PCE loss. The region loss is based on the structural measure SSIM and the regional measure IOU of the images. Different from existing structure loss, we divide predicted map and ground truth map evenly into 4 equal subregions and compare the similarity respectively. The one, on the other hand, will also introduce object level image similarity measures to form an object level loss. Since GT map usually have sharp foreground, background contrast, and uniform distribution, the predict settings map should also have these properties. We use the luminance component of SSIM and the coefficient of variation to model these two properties respectively. Okay, in the aberration study, 4 round reduced MAE greatly compares to 2 round enhancements on all databases. Region level loss and object level loss both help to improve the performance. This is the quantitative experiments with result. MENet has overall best result on 3 benchmark datasets except ESSCD. MENet with ResNet 50 outperforms SOP methods using ResNet 101 EGG16 as the backbone by a large margin for 3 datasets. Inference for a testing image in real time. Here you can see more results showing PR curve in row 1 and FM curves in row 2 for SOD method. From qualitative results, we can see boundaries of the target are more precise and complete for the issues mentioned before. To conclude, we have fully leveraged the human visual system and the cognition mechanisms. A new hybrid loss that measures pixels, regions, and object level similarities. A multi-enhancement network with multi-scale feature aggregation. State-of-the-art result in models using ResNet 50, 101, or EGG16 as backbone. Thank you very much.